Alright, in this video we're going to give a brief introduction to complex numbers, but in order to do that, we need to think really carefully about how real numbers work and how they interact with each other. So we have the number 3 here, and we want to think of every number, like this 3, as carrying a couple of actions, a couple of ways of affecting or interacting with other numbers. So I've actually drawn the number 2 here in green. That's the number 3 is going to act on. Okay, notice also we're using an arrow to represent our number. More on that later. So the first action 3 can do is to add. To add 3 would just be to move a further right by 3, of course giving 5 because, well, 2 plus 3 is 5 after all. But the visual pattern we want to see is addition is all about movement. To add 3 was to move right by 3, and the direction of movement is indicated by the direction of the arrow. So if we change to negative 3, the arrow would turn, indicating that we now want to move left, which is why 2 plus negative 3 sends you to negative 1. So that's really all for addition. I think that one usually is quite clear to you already. The other action that the number 3 can do is multiplication, and that's where we need to think a lot more carefully about it. Okay, so to multiply by 3 is first of all to stretch the arrow to 3 times its length. So we have 1, then 2, then 3 times the original length, arriving of course at 6 because 2 times 3 is 6. So that's the first thing multiplication does. It stretches the length of the arrow. So what's different if we multiply by negative 3? Well, the 3 actually still means the same thing, stretch the length to 3 times the original, landing on 6 again. But what does the negative do? Well, you probably already know that it takes you to negative 6. But we want to now picture that as rotating the arrow across to there. So that's what the action of multiplication is. It is a stretch and a rotate. And it's going to be extremely helpful to almost have those two ideas completely split in your head. Right? The 3 is responsible for the stretch, and that only cares about the lengths of the numbers you're multiplying. Okay, that's why we could just think 2 times 3 is 6 separately to the rotation. While the negative is responsible for the rotation, and that only cares about the direction of the numbers you're multiplying. Okay, and the natural way to specify direction is to use an angle. So notice that the negative caused the green arrow to have to rotate by a total of 180 degrees. So that's what the negative does. It's a 180 degree rotation. Okay, so let's apply this idea to multiplying two negatives. So first, the stretch. This only cares about the lengths of the numbers involved, so only the 2 and the 3 giving you 6. So we draw an arrow going to 6. Then we worry about the rotations. So both the negatives carry a rotation of 180 degrees, giving a total rotation of 360 degrees. Which really means the arrow doesn't end up going anywhere, okay? Which is why you should know 2 negatives multiply to a positive. Or if you wanted to, you could actually have thought of it as negative 2 already pointing left. Then the negative 3 multiplication causes it to rotate another 180 degrees, making it point that way. Okay, it doesn't really matter how you think about it, so long as you see this idea of splitting the multiplying action into a stretch and a rotate. Also, we hopefully see that the convention for measuring angles is just like trigonometry. Okay, positive numbers going right carry 0 rotations, that's 0 degrees. Then we measure positive angles going anti-clockwise, with negative angles going clockwise, going down from right. Okay, so let's bring in the complex numbers now. Now, these are simply numbers that can go up and down as well, not just side to side. That's all they are. Okay, and we're going to start by just drawing some of these numbers and trying to apply what we've just seen, particularly about multiplication, to these numbers. Now note, this is not an XY plane of any sort. These arrows here represent single numbers, just like the number 2 or the number 5, right? But these guys just happen to point up or diagonal or whatever, but they are single numbers, whereas on an XY plane, coordinates have 2 numbers, right? So there's a bit of a difference there. Okay, so let's multiply these two numbers here. Once again, we'll take the green number as the starting point and think about what happens when we multiply by the blue number. So first, the stretch. The stretch only cares about the length, so we see the blue number here has a length of 2. That means it stretches the green guy to twice its length. Notice we've kept the direction steady for now, because now we think about the rotation, so what rotation angle does the blue arrow carry? Well, as we said, we start from 0 degrees, pointing to the right towards the positive numbers. And we see how far we need to swing anti-clockwise. So we see the blue number carries a 90-degree rotation. And all that's left to do is to apply this rotation to the green number, meaning the answer is all the way down here. So multiplying by the blue number had the effect of both stretching to double the length and rotating by 90 degrees. So while it's cool and I think pretty important actually to be able to make sense of this sort of multiplication even with numbers that don't have names, I've just been saying the blue guy and the green guy, we can't stay that way for too long, okay? So a very important number we will meet here is the one that simply takes one step up, and that's going to help us name all the numbers everywhere. We call this guy I, which unfortunately stands for imaginary, which in my opinion is one of the worst blunders of naming in maths history, but it's way too late to change that now. So, like any other number, it's got two actions, addition and multiplication. First, addition's easy, you just follow the arrow, and it tells you to move up one step. Great. Now for multiplication, again we have a stretch and a rotate, so let's start with a stretch. Remember, the stretch only cares about the length of the arrow, which in this case is 1, because the number is a single step, going 1 up, right? So that means you stretch things to 1 times their length, and why that sounds so awkward is that this action does nothing, right? Multiplying a length by 1 doesn't change anything, so actually, this number I carries no stretch. Okay, that's okay, just like how positive numbers happen to carry no rotation, okay? But what about his rotation? Well, it's just like the previous example. If we start with an arrow going right carrying 0 rotation, we spin anti-clockwise and see that he carries a 90-degree rotation. One interesting consequence of this is that when we multiply I by itself, so I times I, or I square, it just means we rotate him 90 degrees again, without a stretch, arriving at the number -1. Now, some people freak out here at this point about having found this mystical square root of -1, and they make such a big deal of it. And yeah, it's important, okay? We use these numbers all the time in very real-world physical things, but this should not be something to be so amazed at, because we're literally just saying that rotating by 90 and then rotating by 90 again is rotating by 180. That's all we're saying. Okay, we should be happy that we can square root negatives, but we shouldn't make it such a mystical imaginary thing. Okay, before we move on, it's probably worth noting that starting from +1 again, rotating clockwise twice would have also produced -1, so that means -I or square is also -1, where -I is naturally the number that takes you one step down instead of one step up. Okay, and that's actually a relief, because it's consistent with what we know about our regular numbers, which is that squaring a negative number produces the same result as squaring a positive, and we see that is consistent even for the i's here. Okay, so let's end by seeing one more multiplication, but we'll actually be able to give our numbers some names this time. So this blue arrow here takes you 3 steps right and 1 step up, so we'd call him 3 plus I. 3 to the right and 1 up. This little yellow guy here takes you 1 step right and 1 step up, so likewise he would be called 1 plus I. And now when we multiply, the really cool thing is we can actually just follow our usual expansion pattern. So 3 times 1 is 3, 3 times I is 3I times 1 is I, and the last one is the one to be careful about. I times I is your double 90-degree rotation, so it gives you -1. So now, we can almost collect like terms, right? But I don't want you to think about it this way. Look, when we say 3 minus 1 is 2, we're actually pulling out of this mess just the horizontal movement. And when we algebraically see that 3i plus I is 4i, what we're actually doing is we're pulling out just the vertical movement. Okay, so feel free to use your algebra stuff, but it's also so important to be aware that there is this geometric thing happening behind the scenes, and actually part of why these numbers are so powerful is the fact that it gives an algebraic structure to geometric things like moving and rotating and all that. Okay? Alright, so how would we draw this answer? Well, 2 means move 2 to the right, so there it is in green. Then 4i means go 4 steps up, so we shoot up to there. Okay? And let's finally finish by confirming that this all actually works the way we expect it to by comparing with the whole stretch and rotate story. Okay, so we have the blue number 3 plus I. That again means 3 across and 1 up, and we're labeling them to easily see that the length of this arrow, this blue arrow, comes from Pythagoras. So 3 square plus 1 square is 10, meaning the length of the arrow is the square root of 10, and that must be our stretch. For the angle of rotation, we'd actually need to use a bit of trig. Hopefully you can see that it's the inverse tan we need, so the angle would be the inverse tan of 1 over 3, which works out to be around 18 degrees. Now for 1 plus I, the yellow arrow. That means 1 across, and the same 1 up. So we do Pythagoras, 1 square plus 1 square is 2, so the length is root 2. For the angle, you shouldn't even need a tan, it's diagonal, so it must be 45 degrees. Okay? And let's do this one last time for our green answer, 2 plus 4i. It is 2 across, it is 4 up. So Pythagoras, 2 square plus 4 square is 4 plus 16, which is 20, so the stretch is root 20. And for the angle, we'd have to use inverse tan again, with 4 over 2 this time, which if you check in your calculator happens to be the 63 degrees, okay? But I hope you've noticed that all of this checks out. Why? Look first at the stretch lengths. Root 10 multiplied by root 2 is indeed root 20. And now look at the rotations. A rotation of 18 degrees followed by a rotation of 45 degrees is indeed a rotation of 63 degrees altogether. Okay, and we can see that the little blue angle there does fit perfectly inside that gap. And I reckon that is very cool. If we think back to the algebraic expansion, right, to think that that expansion pattern was hiding all this information about Pythagoras and roots and trig and angles and all that, and that's all just behind a simple algebraic pattern. Okay, again, this interplay between the algebra and the geometry is just one of the things that makes these numbers so powerful. Okay, so hopefully we'll see more later, but that's all for now. See you around.